So let's go on to another problem. Okay, this says a reversible heat engine operates between two systems at constant temperatures of 600 degrees centigrade and 40 degrees centigrade. The engine drives a reversible refrigerator which operates between systems at constant temperatures of 40 degrees centigrade and minus 20 degrees centigrade. The heat transfer to the engine is 2000 kilojoule. The net work output of the combined engine and refrigerator is 350 kilojoules. We are asked to evaluate the heat transfers involving the refrigerator. So let's see what we can do here. So we have a reversible heat engine, which essentially is like, say, a Carnot engine operating between 600 degrees centigrade. So I'll convert it into Kelvin. And 40 degrees centigrade. So we have information given. This is for the engine. So we have TH is 600 degrees centigrade. It's about 873 Kelvin. TL is 40 degrees centigrade. It's about 313 Kelvin. So this takes in heat of QH, let's say, give some heat of QL, it rejects and does some work, which is W. That's the idea of an engine. So what it says is that this engine drives a reversible refrigerator. So the work from here is used to drive some refrigerator. So I am using this work to drive the refrigerator, which operates between systems at constant temperature of 40 degrees centigrade and minus 20 degrees centigrade. So for the refrigerator, it works between some low temperature. I'm going to call this TR refrigerator, between a low temperature of minus 20, which is essentially 253 Kelvin, and 40 degrees centigrade. So the refrigerator over here this is the it's a reversible heat engine, but I'm going to call it E anyway because I'm going to use R for the refrigerator. So this is the heat engine, which is reversible. Carnot heat engine. It also drives a reversible refrigerator. Okay, so both are reversible. So we can call both as Carnot engines and Carnot refrigerators. So this takes in work, transfers some amount of heat from the low temperature reservoir, which is 253, to the high temperature reservoir, which is at minus 40, which is at 40 degrees centigrade, or essentially 313 Kelvin. So this is essentially what we have. The heat transfer to the engine is 2000 kilojoules. So QH, which is what we are giving the engine, this is given as 2000 kilojoule. The net work output of the combined engine refrigerator is 350 kilojoules. So what I am doing here is I am running an engine, taking some of the work and giving it to the refrigerator. It says the net work output of both of these put together is 350, which means when I put this together, I still have some work which is coming out. Some of the work from this engine I am using to run the refrigerator. there is still surplus work, which is essentially 350 kilojoules, which I can use for something else. So, we are asked to find out the heat transfers involving the refrigerator. So, this QRH and this QRL is what we are asked to find out. So, this is actually pretty typical in some sense, because we have a heat engine, we have some high temperature source. For example, we burn coal and we produce steam or something like that, and we run this heat engine between this high temperature reservoir and let us say the ambient or the atmosphere at close to 40 degrees centigrade. So, this is one process. In this we are producing power. Some of this power we are using to run a refrigerator. For example, you have a refrigerator at home. The refrigerator at home takes heat from the inside of the refrigerator, which is cold, which in this case is at -20, and gives it out to the atmosphere, which is at 40 degrees centigrade again. So, this is close, this is like the atmosphere at 40 degrees, this is also the atmosphere at 40 degrees. So, in the engine we are taking heat at high temperature and running the engine between the high temperature reservoir, the atmosphere, and here we are taking out heat from the refrigerator and running the refrigerator between the low temperature reservoir and the atmosphere. So, something like this is what we would do. So, what it says is the refrigerator is also reversible and the heat engine is also reversible. That is something which is we can make use of, and we know the amount of heat transferred QH, we know this is 2000. So, we are asked to find out these values. So, if we look at only the heat engine, we know the efficiency of the heat engine is essentially 1 minus QL by QH, taking only the absolute values, and we know this is also equal to 1 minus TL by TH, or essentially for the reversible heat engine QL by QH is TL by TH. So, I can find out, I know TL which is 313 Kelvin, I know TH which is 373 Kelvin, I know QH which is 2000 kilojoules, I can find out QL. Which comes out to be 717 kilojoule. Essentially what I am trying to do is find out the total amount of work which this engine produces. If I subtract from that whatever is surplus, then I know the amount of work which goes here, and knowing the work and knowing the temperatures, I should be able to find out the heat transfers. That is the general idea. So, I have got QL, I have QH. So, the work from first law, sigma W is sigma Q, or W equal to QH plus QL with the appropriate sign conventions, or acknowledging that QH is positive coming into the system and QL is negative going out of the system. This is QH minus mod of QL, taking the signs into account. So, essentially W is QH was 2000 kilojoule, QL we just found as 717 kilojoule. So, the work produced by the heat engine is essentially 1283 kilojoule. Out of the 1283 kilojoule which this produces, 350 is going out. So, the remaining goes to the refrigerator. So, the work input to the refrigerator is essentially 1283 minus 350, which is essentially 933 kilojoule. This is the work going to the refrigerator. The value of this work is positive for the engine, it is negative for the refrigerator. For the engine, it is work done by the engine on the refrigerator, it is positive. For the refrigerator, it's work done on the refrigerator by the engine and it is negative. So, that is also something we have. We also have, if I apply the first law for the refrigerator, so I see W taking only the values of the work. So, I see W is coming in, QR is going in, and QRL is going in. So, QRH must be equal to W plus QRL, or taking into account the signs already. So, if I apply first law, I would have sigma Q is essentially sigma W. So, I would have QRH plus QRL equal to WR. Over here W would be negative because it is work done on the refrigerator. QRL would be positive, work coming, heat coming in. QRH would be negative, heat going out. This would be negative, this would be negative, this would be positive. So, taking into account all of those signs already, what I have is essentially, so this is negative, this is negative, this is positive. So, taking into account all of those signs, what I have is W plus QRL is equal to QRH. This requires the correct sign convention. Here sign convention has already been taken into account. So, this is essentially what I see, or essentially W is QRH minus QRL. This is anyway positive, I do not need this. This is, I can put the mod signs just to remind me that I have taken all the signs into account already. So, the difference in this is essentially 933 kilojoules. That is one thing I have. Another thing I have, this is it's a reversible cycle. So, since it's a reversible cycle, what I know is that QR for the refrigerator, ratio of the heat transferred should be equal to the temperature ratio of the temperatures. So, this is essentially 313 and 253. So, I have the ratio of the heat transferred to the ratio of the heat rejected, the heat transferred out at rejected at high temperature to what is transferred in at low temperature. This is essentially 1.237, I am going to write it as 1.24. So, essentially QRH is 1.24 . So, I have this equation here, so I am going to substitute this in this. So, QRH is 1.24 QRL minus QR comma L is essentially 933. This is 933 divided by 0.24, which is essentially 752.4 kilojoules, and this is 1.24 times QRL from this equation 2 over here. I think I made a mistake in this calculation here. This is not 752. This is 3887.5. and this is 4820.5. And the difference between these two should be essentially 933. That is what we get. So, what we see is that we have in this case a reversible Carnot engine which is running a reversible refrigerator and also giving out some work. So, because they are reversible, we have used this kind of expression here. We have also used the first law for a cycle, and using both of those we have been able to get the values of the heats transferred by this refrigerator.